Okay, thanks. So yeah, I'll talk about work with Moses Charikar, and I want to make this as interactive as possible, so feel free to stop me at any moment. I guess before we begin, maybe just quick show of hands, how many people are aware of the Johnson-Lindenstrauss lemma? I assume most of you. Okay, how many have used the Johnson-Lindenstrauss lemma in a paper? Okay, cool. Okay, so we'll go through it pretty quick at the beginning just to set up kind of the notation and the problems that we'll be talking about. So the Johnson-Lindenstrauss lemma is, well, the clicker is not working. This. Okay, there we go. Okay, so the Johnson-Lindenstrauss lemma, is this theorem about high-dimensional Euclidean space. And really, it says that if you take X is any subset of n points in Rd, so these are d-dimensional vectors, there exists a map pi, and now throughout the talk, pi is always going to be my JL map that maps Rd to Rt, where now t is much lower dimension. It's dimension just log n over epsilon squared, such that for any 2 points in your set x and y, the Euclidean distance between x and y is approximately preserved up to arrow 1 plus or minus epsilon after you apply the map pi. Okay, and in fact, the proof of JL is actually, we have a very explicit random map. If you multiply your vectors by a random matrix, where the matrix is T by D, then that projects all your points down to RT, and this, if you set T to log n over epsilon squared, will satisfy these guarantees with high probability. Okay. So here's the motivating question. We're going to ask, to what extent can we use the Johnson-Lindenstrauss lemma beyond just preserving pairwise Euclidean distances? Or more generally, if you start with any computational problem in RD, going to be some problem involving Euclidean distances, before you even begin to think about algorithms, can you sample a random Gaussian matrix, multiply all your vectors by this matrix? Now you got the same computational problem, but in a much lower dimensional space, RT, such that if you solve the problem in RT, you would approximately solve the problem in the original space. Or more concretely, you tell me the problem, you tell me n, d, and a parameter epsilon. How large does t need to be such that I preserve a solution to 1 plus or minus epsilon? Okay, so the rest of the talk, I'm going to be talking about some algorithms, but really the theorem is just what happens when you apply by Gaussian matrix. Right? So the algorithm is just take a random projection. Okay, so let's get warmed up, and I want to tell you about 2 Euclidean optimization problems. They look very similar, but actually they're going to be very different. So here on the left is the one median problem. So imagine x points x1 through xn. This is your data set. And what do you want to do? You want to try to find the center. So you minimize over any point c, and c is an arbitrary point, which minimizes the sum of distances to that point. So c would be like a representative. That's a one median problem. The one medioid problem, it's very similar, except now c can't be arbitrary. It has to be one of your n data set points. Okay, so the picture is just, this is like a potential center, and here it has to be one of your data set points. Okay, so here's a question. Can you apply Johnson-Lindenstrauss to these optimization problems at all? I claim one of these is actually corollary of the Johnson-Lindenstrauss lemma. The other one is not so clear. Anybody want to take a guess as to which one is easy and maybe a simple argument? Sorry? Yeah, exactly, right? So the medioid, if you project it down to log n over epsilon squared dimensions, then you actually preserve all the distances between the points. And because the center is one of these n points, you've preserved all distances. Therefore, the minimum over all possible centers is an approximation. Okay, it actually turns out that you actually need this log n over epsilon squared for the medioid. And if you project more aggressively, there's going to be one point of these centers which actually gets the average distance smaller by a factor of 1 minus epsilon. So this log n is actually tight. Now for the median problem, here it's not so clear whether you can apply the theorem at all. right? The reason is that this center is arbitrary, and you can't, Johnson-Lindenstrauss doesn't say that you can preserve all the possible centers. Nevertheless, you want to say that for the minimizing one, you actually do preserve the cost. And in fact, what I'll tell you in this talk is that there are techniques that actually you can do much better than what you could do in the medioid, just because the center was arbitrary. Okay.
Right.
Yeah.
So, but what does it even mean to say you're finding the median, in the sense that the solution may not map back to the original space, right? After doing the projection.
Good. So yeah. So what this is saying you start with endpoints, sample a Gaussian matrix where T is 1 over epsilon squared, and wherever you see X here, you replace it with pi of X. And now C doesn't vary over RD, it now varies over RT. And you minimize that, then the cost is up to 1 plus or minus epsilon, the same as that of the original. But it's saying that this will not hold with probability 99%.
So the objectives are preserved in value,
yeah.
But it doesn't necessarily mean that you can get a solution to the original problem.
That's right. Now we're working in a lower dimensional space in RT. Okay, so that was one. Yeah.
What is your soft in?
Oh, in just the parameters of the problem. So I think I'm going to lose a log 1 over epsilon.
So it's not log n.
It's not log n. That's right. So whenever I use the tilde notation, it'll always be log factors in the thing. Yeah. Good. Okay. Now that we've seen kind of one problem of this sort, I'll give you another problem. Is just like a one-dimensional extension. So this is a one subspace approximation problem. So what do I want to do? Now I have a data set x1 through xn, and I'm going to approximate it by a subspace of dimension at most 1, so a line. Okay? And now here, the subspace is arbitrary. Now think of the green point as the origin. And the one column subset selection, this is the same problem, except that now my line has to go through one of my endpoints. Okay, so the picture here is we're trying to find a line in the space which minimizes the sum of these black lengths. And the one subset selection, the line has to go through one of your data set points. Okay, and now you can probably guess again. It's not a super trivial exercise, but if you've heard the word subspace embedding, then you can apply JL to log n over epsilon squared. You preserve actually all distances to all lines through these points. And we'll show how to do much better. We'll get a little bit worse than 1 over epsilon squared. We'll get 1 over epsilon cubed, but completely independent of n. Okay, so here's how the rest of the talk is going to go. I'm going to formally define the problems that we're going to study. These are going to be extensions of this one median and the subspace approximation problem. And then we're going to talk about some of the techniques that are involved. Yeah.
Sorry, quick question. On the previous slide, you could have this problem generalized to be a k-dimensional subspace, and then
yes.
What's the dependence of k?
Yeah. So I'll get to it in a second. And yeah, so I'll describe all the problems that we'll study, and I'll tell you the prior work, what was known. And then we're going to go through the techniques. I'll tell you this, maybe it's kind of a conceptual proof. It's not, there are some core ideas, but I'm confident that you could kind of recreate it for yourself. And then some open problems. There's still a lot of things. In fact, all the results that I'm going to present, I don't think they're tight. But before we get into it, let me just tell you the conceptual takeaway of the talk, that in the analysis of Johnson-Lindenstrauss, I'm going to use algorithms for constructing coresets. And if you haven't seen what coresets are, I'm going to go into it. They're like this really cool tool from computational geometry. And I'm going to use the algorithms for coresets to analyze what happens when I multiply by a random matrix. Okay? Okay, cool. So let me tell you, I guess, the problems. And the first one is just the KZ clustering problem is an extent or a generalization of the K median problem, or the one median that we saw. Yeah, with the question. Okay. So the input, and my input is always going to be this data set X, X1 through Xn. These are endpoints. Now I get a parameter K. K is the number of clusters. And Z. Z is going to be some measure of how your cost changes with respect to outliers. And what is the objective? Well, now you get to pick not one center, K center, C1 through Ck, and the cost is how each point xi chooses its closest center, so you minimize over j for c1 through ck, and you pay the distance to the z power, and then you take the power 1 over z. Okay, when I described k, the one median, this was z equals 1 and k equals 1. But as you vary z, you get some of these classic clustering problems. So maybe for z equals 1 is k median, for z equals 2, you get the k mean problem. And now for z equals infinity, you can think of this sum as being dominated by the largest quantity. This is the k center problem. Okay, and just again, what are we studying? We're sampling, we're asking what should t be such that if you sample a random matrix pi, and whenever you saw x, you substitute by pi of x, and whenever you saw rd, you substitute by rt, but now this optimization is approximately the same as the original one. Okay, this is now the case subspace approximation. This is what Ines was asking. Again, input x, k, and z, but now k is a dimensionality of my subspace. So what do I optimize over? I pick a subspace of Rd of dimension at most k, and the cost is the sum of distances from x to the projection of x onto that subspace S. Okay. Again, pick to the power of z, and all raised to the power 1 over z. And again, as you vary z, you get these like classic subspace approximation problems. When z equals 2 is known as the low rank approximation. If you think of z equals infinity, let's say you get these notions that are studied in computational geometry, like the radii or the width of points. If k was 1, you're thinking of a line and you're trying to fit a cylinder that contains all your points. But again, the same problem. We're now going to sample pi, you substitute wherever you saw x, you substitute pi of x, and now the subspace runs over RT. Yeah, are there any questions? Okay, one final problem, and now I'm going to combine both the KZ clustering and the subspace approximation, but I'm going to do it just for lines. This is known as a KZ line approximation. Again, the idea is you want to partition your points into K parts, and for each part, you approximate the part not by a point, but by a line. Okay, so this is kind of what this picture is showing. Okay, this is part of what's known as projective clustering. You can even think more generally than lines. You want to partition your points. For each part, you approximate it by a low-dimensional subspace. But already the results are going to degrade enough for K-line that we didn't do it for projective clustering. Okay. Any questions on the problems? Yeah.
It seems like if you're doing dimensionality reduction and then finding a subspace, like you're doing like a coarser dimensionality reduction and then a finer dimensionality reduction.
That's right. Yeah.
So can you like repeat that over and over again and say, oh, now that I have like a better like subspace, I can now plug that in and get an even better subspace?
Yes, but yes, you could do that. But kind of what we're focusing on is just preserving the cost of the optimization. Imagine that, I don't know, if you're doing you're trying to find the best k-dimensional subspace, in terms of this problem, k is always a lower bound because the cost of the entire space will be 0. So yeah, you can, I mean, in practice, you can think about doing this, but from theory, it still makes sense to ask this question. Okay. So we're not the first to ask this question. I think Erik and Kostya had this paper on it. This is how we started studying this question. But there's a big difference in these kind of problems of whether you're studying the particular case when z equals 2 and for general z. Kind of, we already saw that for z equals 2, you get the k-means problem, and for the subspace approximation, you get a low rank approximation, and z equals 2 has some nice algebraic properties that you can exploit. And now for this problem, for k-mean, there was quite a bit of work done. But in this paper by Charikar, Rosenstein, they show actually you can already get log k over epsilon divided by epsilon squared. And now for the specific case of z equals 2 for low rank approximation, there was this paper of Cohen, Elder, Musco, Pursue that got a bound of k over epsilon squared. Okay, so actually, this paper shows something much stronger. I'm going to get into it toward the end of the talk. But for general Z, what was known? Well, actually, the techniques they developed here, they generalize for general KZ clustering, and they get this kind of guarantee. For KZ subspace approximation, you kind of lose the algebraic properties of Z equals 2. There was a bound, but it got a dependence of log n. Somehow, even log n was kind of interesting. And here are kind of our new results. Now, I don't want to focus so much on the quantitative bounds. The kind of the key takeaways is that for KZ clustering and subspace approximation, the bounds are completely independent of n as well as d. So somehow this is saying, look, for these problems, the dimension that you need to project is completely independent of the problem size. It just depends on the formulation of k, z, and epsilon. Okay. Now we can say for k line approximation, we're already starting to degrade. We're getting like k log n bound. Yeah. The nice thing is that all these results are going to follow basically from one kind of general principle, and that's what I'll present.
And the K-line approximation, I guess, so that's an upper bound? But
Yes.
Or do you also think it actually should depend on it?
No, I don't think it's enough. So we show upper bounds, but in general, there's no reason why for K-line approximation, you shouldn't be able to get log K over epsilon squared.
Can you remind me of the subspace approximation? What is the dimension of the subspace?
Yeah, I kind of overloaded the notation. K in subspace approximation, K is a subspace. In clustering is the number of parts, and that's why here I'm only focusing on the line. So this would be K parts, one-dimensional subspace. You can ask more generally, K parts, J-dimensional subspace. I don't know how to do this. Okay. Any questions? Okay, good. So let's get into the techniques. And here's what I'll tell you what core sets are, kind of what makes these problems special, and how we're going to use core sets to analyze what happens when you take a projection. Okay, just to remind you of the problem, we're just going to stick to the one median problem. I think already here we can kind of, the main ideas kind of shine. So we start with the data set. You want to find the center. The center is arbitrary. The question was sample a map, substitute, and prove approximate equality on the optimization. Okay. And I promised that 1 over epsilon squared bound. Actually, it's going to be very easy to show a poly 1 over epsilon bound. That's what we're going to do. You can kind of use the techniques in Makarichev-Rajanstein to kind of shape this poly 1 over epsilon to 1 over epsilon squared. Okay, good. So let's do it. What do we want to show? We're starting with RD. We want to apply this map and go to RT. And whenever you're trying to show kind of approximate equality, there's really two directions. And conceptually, we want to say that the cost of the optimization in the projected space doesn't increase and it doesn't decrease. Okay, there's one direction that is an easy direction, and the other one is a hard direction. Okay, we're trying to we have a minimization problem, and intuitively, whenever you have a minimization problem, it's always easy to upper bound it, right? You just need to exhibit a solution, and that's a proof that the cost can only be smaller. So what's the easy direction is to show that, and even it's quantitatively easier, if we took a projection, the cost in the projected space doesn't grow by more than a factor of 1 over epsilon. Okay, here I just need to start with something I understand, and then sample pi and show you here's a solution, and the cost is bounded. Okay, so what are we going to do? How do you prove this inequality?
Wait one second. When you say cost, you mean the minimum objective value?
Yes, the cost of the minimum objective value. That's right. So how does this work? Well, imagine I know my optimal solution. I find my true optimizing center, and that's the cost in the original space. Well, now I sample pi, and I look, where does pi land? This gives me a point. And now here's a potential solution for that point. I'm just going to compute what is the cost of that point after applying the projection. The good thing is that because the point is independent of the map, I'm thinking of the center and then applying pi and getting pi of z. I can use the distributional properties of pi of z to understand how the lengths of these black lengths correspond to the lengths of the original lengths. It turns out it's actually not hard to show that actually just following kind of the properties of the Johnson-Lindenstrauss lemma that pi of x to pi of z is at most 1 plus epsilon times the original distances, and that gives me a candidate solution. Therefore, the optimization has to be less than that. Okay. Was that clear?
Sorry.
Yeah.
I mean, you're also projecting all the points, right? But is it the fact that you don't need all of the distances to be preserved and you only need it on average?
Yeah, good. So here I'm saying, so the distance between xi to zi, if I sample pi, then the expected amount of distortion, it's an expectation 1, so an expectation, the sum is preserved, so then there's some like easy Markov inequality. Yeah.
I'm confused. Like if I know that the operator norm of pi in this right hand side inequality is at most 1 plus epsilon, then I get a point by point guarantee from xi to c being distorted by at most 1 plus epsilon.
So you can't quite get a point by point guarantee because that would involve preserving n many distances. But here it's not, I don't need a point by point guarantee. I just want to say that the sum of the distances is preserved.
I don't need to preserve distances, right? I just need to show they don't expand by 1.
Yeah.
But that seems to be point by point. They're not expanding if pi has this property.
So I think, I mean, there are some distances that may get distorted because you're trying to preserve n things. You can't union bound over n things. Nevertheless, the sum is an expectation, what it should be, and then you just need to think about one quantity. Okay. It's important that I'm not preserving point by point, I'm just preserving the sum. Okay, but that was kind of the easy direction. So why is the opposite direction hard? Well, really what I would want to do is I want to do the argument in reverse. I want to start with a solution here and now show that there's a solution in the original space whose cost is not that much bigger, that guarantees that my solution hasn't shrank too much. But the problem is that when you solve for the center, for the optimum here, this red point actually depends on pi. Right? You can think of like the optimization will take advantage of some distortions, and imagine you had a bunch of points, there's going to be some distortions. Some get closer to each other, like bam, that's where your center is. And now, how do you argue copycat? In particular, when you have that center, that depends on pi, you can no longer use the distributional properties of pi inverse on the data set points. Right? In some senses, you kind of fix the randomness by finding the center of y pi. Okay, so the entire game here is how do I, before I sample pi, I need to say, let me find some properties of pi, which happen with some large constant probability, such that if you have these properties, then you can take the optimum here, and you can find an optimum on the other side whose cost does not decrease too much. Okay. And this is what the notion of coresets is going to come in. Okay, so maybe by a quick show of hands, how many have seen coresets before? Okay, good. So coresets, just by itself, I think this is very interesting. It's maybe pioneered in this paper by Agarwal, Harpalet, and Varadarajan. And you should really think about coresets as saying, okay, this whole talk has been about dimension reduction. I've been thinking about D as my parameter. I want to decrease D to T. Well, these guys were studying, okay, let's first, can we decrease N? So N is my size of data. Can I decrease N to some smaller data set? So that's why I'm saying it's a data set reduction technique. So they were asking the following question. Imagine you have this problem of K clustering or subspace approximation. And I have it on my original data set, it involves endpoints. Is it possible to find a subset of my data, and maybe attach weights to the data set, such that if you solve the problem on the weighted data set, it would approximately tell you a solution to the original data set. Okay, so this would reduce the dependence from n to whatever the size of the core set is. Now I'll go into it a little bit later, but it turns out that we've gotten really good at understanding how to build these core sets. And there's kind of surprising results in saying, look, for this median problem, you started out with n data set points. There exists a core set, there exists a subset of my data S, but now I attach some weights W, such that if you solve the analogous problem, but now on the set of size S with the weights W, the cost of the optimal solution is preserved up to a factor 1 plus epsilon. The benefit is that now S is of size poly 1 over epsilon. Okay, this should be surprising. You start out with all these points, but now you can find just a subset of size which is completely independent of n, completely independent of d, just poly 1 over epsilon, such that these are some sense the important points. And if you solve your problem there, then the cost of that is the cost of the original problem.
I have a tended question. How related is this to sampling? Because it feels to me that it's kind of like a sampling problem.
Yes, that's exactly the case. And the way that we'll build these core sets, and I'll show you a little bit later how to build it, these are exactly done by sampling according to the right distribution. Well, we'll see. But conceptually, when you have a core set, there's a very strong message attached to problems for which you can build, even existentially, a core set. It says, look, your original problem, it looks like it depends on all its data, but really it does not. Really, there were some points such that if you took those points and only solved the problem with respect to those points, then you would solve the problem to the original problem on size n data set. So this is kind of the intuition that we're going to try to exploit. It's like if your problem has a small core set, there exists a subset of its data. So maybe we could just have JL preserve the pairwise distances or like the properties of that smaller data set. And just by preserving that, we'd be able to preserve the cost over the entire data set. That's really the intuition. That's what we're going to formalize. Any questions? Okay, so if you've zoned out, this is really the most important slide of the entire talk. It's a proof diagram where I'm going to show you how to go from core sets and use them to analyze dimension reduction. And the picture is this. We start out with the original data set X. We apply pi and we get the JL data set. And now I don't understand this arrow directly, but I have a convenient tool, which is to run my core set algorithm to find the subset of points which are really important. The subset x1, xi1, when now m, the number of points is just poly 1 over epsilon. Okay, so now you've decreased the size of your data by generating this core set. And now I'm just going to look at, okay, what would have happened had I applied the JL, the transformation just to that core set. The benefit is that this arrow only depends on the points x1 through xm. Okay, in fact, just as a very crude bound, you can think of saying, okay, I generate poly 1 over epsilon points. Imagine that Johnson-Lindenstrauss preserved that subspace spanned by the S points. Okay, this is a constant size subspace. I could hope that JL preserves the entire thing. And that means that that's basically going to tell me that I can go back and forth in this arrow by only losing 1 plus or minus epsilon factor. Okay, and what would be really nice is that if this diagram commuted. So if I could show that taking my core set and applying JL, if this was indeed a core set of that, had I applied this algorithm here, I would have done the same answer, then I'm in really good shape, right? Because then I want to understand something here. What do I want to do? I start with my optimal solution here, but I say, hey, actually, look, that core set was a core set for the JL data set, even though you ran it with the algorithm there. So the solution is good for that core set. And here you had a subspace embedding. So this was, you can look at the solution on the original core set. But this was also a core set, so now you can analyze solution. So just the goal is to start with a solution here and follow the arrows while only decreasing the cost. That means that you started with your optimal there. If you're able to follow the arrows, you have found a solution in the original space whose cost is only smaller. Therefore, the minimum in the original space can only be smaller, and that's the reverse direction. Okay, I'm gonna leave this up, Ben.
Wait, I may have missed this, but so you constructed the coreset and then you did JL on the coreset.
Yeah.
That's potentially not the same as that's potentially not a coreset for the JL dataset.
That's right.
So when you do the reverse direction, you're constructing a different object.
No, good. So yeah, so I said it would be nice if the diagram commuted. And if the diagram commuted, if I could prove that kind of running the coreset algorithm on my original data and then applying JL, if that thing is a coreset for the original data, then I'm in good shape. Right? Yeah. Okay. And what the nice thing about this is that I didn't mention anything about the problem. It was just about constructing the coreset. This has nothing to do with clustering or subspace approximation. And in fact, all the results are just by looking at different constructions of coresets and saying, oh, what do we need to maintain in this arrow in order to go back and forth?
I didn't follow, maybe you're gonna get to it, why you can go back and forth from core sets.
Oh, between the coresets. Okay, good. So now this is a small data set. Think of this is this is size poly1 over epsilon. This is a constant. So now I'm saying, what happens when I apply JL on a constant dimensional space? And here I can hope to preserve my entire, if I look at the subspace spanned by S in the original space or after the projection, I could hope that this subspace is basically an approximate isometry. So for any linear combination in here, this is just, I'm looking at a constant dimensional thing. It's like the first.
I'm sorry, just,
Yeah.
So you had dimension D.
Yeah.
You play this core set that you're still in dimension D. But you have a
Still
small
in dimension
number of
D.
points.
Yes.
So when you say dimension now, you mean something else.
So I'm saying,
You don't
look
need
at this, look at the subspace spanned by the points. Okay. Now I'm in dimension D, but I only have m points. So the dimension of the subspace is at most m.
Yeah.
So now I look at how JL acts on this m dimensional space, and I'm saying, imagine this was an isometry. For this, I would say JL here is like T would be set to m divided by epsilon squared. But the point is now the dependence on T is just with respect to m, not with respect to D or n.
So why don't you take T equals M?
Yeah, so for this argument to work, you would set T to be m divided by epsilon squared. So yeah, it's like you have a d-dimensional space, but you are looking at a constant number of points. It's a constant dimensional subspace. And now you're saying, what happens to a constant dimensional subspace when I apply JL? And because it's just a constant dimension, then you preserve all the points up to 1 plus or minus epsilon.
So I don't quite understand why T equals M and get a precise isometry.
When T equals M,
So you said T
Yeah,
is M
probably
divided
if-
by epsilon squared. That's even
Yeah.
larger than M, and it's not an isometry. I don't
that's
know.
right, yeah.
When you
Maybe
said
it's
T to be
because
equal
this is
to
the
one.
difference between random Gaussian matrix and like a strict projection.
These dimensions are different, right? Like, so if you set D to be just equal to M, the left-hand side is in D dimensions, like your points are D dimensional, on the right-hand side, your points are D dimensional. They won't be the same.
No, I think that,
No, you can come up with a prediction. It is exactly.
yeah, you can come up with a projection, but
Projection is
because I'm,
literally the span of the subspace, right? But you can't do it efficiently is the point.
for the random Gaussian matrix, if you want to preserve an m-dimensional subspace and you want to use this random map,
So this has
you
to
need
be
m to be,
not dependent on.
because the map kind of, the map didn't know about my algorithm. It was completely oblivious. Yeah. But if you looked at the points, then yes, you could project to m dimensions and just focus on that. Okay. Okay, so that was the plan. Now let's do this plan for the one median problem. I'm just gonna run through the diagram that I had. What's my success event? So I sample pi, I need to identify the properties, and then if these properties succeed, then I can peel back every point. So one is I'm assuming that I run my coreset algorithm, it succeeds on the original data, and I'm also now imagining for a second that it happens to be the case that the coreset algorithm applied to pi of s is also a coreset for the JL dataset. Okay, if that was true and JL was a subspace embedding between the coreset, the span of S, and RT, then I need to tell you how to peel back the solution. Okay? And this is where I'll set T to be the size of S divided by epsilon squared. The point is that now it depends only on the size of the coreset, not on N or D. Okay, so let's do it. You start with the optimal there. Imagine all these things are fixed. Everything, the picture, there's no more randomness. So now I find the optimum over all the data set. Now I took a coreset. So pi of s was a coreset, so really I can evaluate the cost of my green point just with respect to the sampled yellow points. Okay, but now I've made these bolded because they're weighted. It's like the sum of the lines. And now I can just move the point to the span of that subspace. I only decrease the cost. Remember, I want to move while only decreasing cost. But now the solution, this red point, lies in the span. And because I had a subspace embedding, I can find that same point in the original space. And sometimes you can think of writing this point as a linear combination of S. And there's a corresponding analogous linear combination of S in the original set. And these lengths are preserved because it was a subspace embedding. But now these points were also a coreset. So the sum of these weighted lines is the same as some of the original lines. Okay.
Yeah. Conceptual question. So on the right hand side, you have weights for each of the points, right? Like you're taking a weighted average in the subspace.
Yeah.
Like
Yeah.
These are weighted.
These are weighted points. That's why I'm making the lines kind of have bigger width for bigger weight.
Right. And then when you go back, what happens to the weighting?
The weights are the same. So the weights, and I'm saying the coreset algorithm, it would have output the same subset of points with the same weights in the original space or in the projected space. So it's literally the same linear combination, but here my points were in RT, now my points are in RT. Any other questions?
If it's not too lengthy, can you say why this kind of approach doesn't work for the original?
For the meteoroid problem?
Just the original problem, like why can't I do the convex combination trick? You're expressing the point of the convex combination going back just with the original large set of points.
Yeah, good. Because like if I start here and you say, oh, this point lies in the subspace of everything, preserve it. Yeah, good question. The point is that I can't say anything about that linear combination being preserved. The event I fixed was that it was important that I kind of fixed pi. And then I look at the optimum. I represent it as, okay, wait, so, sorry, let me know if I'm answering your question. If you had a point, you write it as a linear combination. It's not clear that the corresponding linear combination has all the distances preserved. Like in some sense, it was, you want to be able to use the randomness, but you want to use it in like a,
When you express the linear combination as a linear combination, then you bring it back.
But now that linear combination depends on pi.
But you've really rewritten things in terms of the original points.
Yeah.
And those distances are preserved.
But the weights in my linear combination is a function of pi.
Yeah.
So now I'm applying the inverse but this is not the guarantees of JL, because in some sense you want to say for a fixed point, which is independent of pi, now sample your randomness and see what happens. Here my point depended on pi. The thing about what I'm saying is that if JL preserves the entire subspace of like a few number of points, this event doesn't depend on the optimum that I'm going to find. So I'm saying I'm fixing this event, and now as soon as that's true, I'm going to be able to like kind of peel back any linear combination inside the small span.
But building on that question, you could preserve the entire subspace by just setting phi to have, d over epsilon squared.
D over epsilon squared?
Like the subspace on the right is just d-dimensional, right?
Yeah.
So you could preserve every point in the subspace.
But no, but T is a quantity I want to optimize.
Sure. I'm saying like if you allowed me a worst bound, there you get a subspace embedding for dimension d.
A subspace embedding, but you need to set T.
Yeah, you want the subspace embedding from the left, not from the right.
So, okay, maybe we should do this also.
Yeah.
Like, I'm just saying, like in your previous trick, you were applying the subspace embedding to the core set on the right hand side.
On the core set, I'm saying I'm applying the subspace. I'm sampling the core set.
Yeah.
And I'm saying this spans a low dimensional subspace. I sample pi, and as soon as pi is a subspace embedding on that small set, then I'm good. That's my success event. This doesn't depend on the optimum on the right. Okay.
The one I think it certainly will project some point to the same point because of different dimensions, right? But for the small subset, they have like almost identity.
Yeah, the point is that kind of after this event, the randomness in pi is completely fixed. Okay, that's important because now when I find the optimal solution, this depends on pi, but in order to peel it back, I don't need to use any more randomness. I think that was the. Okay. Now there's one thing to notice is that maybe we didn't use the full power of the core set. We just used that for the optimal solution, pi s preserves the cost over the JL dataset. Okay, so I didn't need that if I solve, I just needed, look, if you solve the problem on the entire dataset and you look at that cost on pi of s, that cost is preserved. It doesn't necessarily mean that if I solved it for pi of s, that it would be a solution for pi of x. But anyways, this is a minor point. It'll only simplify our arguments. Okay, yeah, that was the point. Right, I mean, I started here. I needed to kind of go back. All I needed to say was that this inequality was true only for the optimal. Okay, it could be there are lower cost things here, but I'm allowed to decrease the cost. Okay, so really the final step is just to show you that kind of these core set constructions commute. That if I took a core set on the left and a core set on the right, if up to some pi, then I would still recover something for which the optimal solution, you guarantee that the cost on pi of s is approximately the same as pi of x. That's the final step. Okay, so now we'll get into what the core set constructions are. And yeah, there's like a natural kind of approach to generate core sets is just to proceed by taking a random sample. Right, so you start with the original data, you could random sample, look at a subset of like uniform random sampling. This obviously commutes, right? A random sample on the left is the same as a random sample on the right. The issue is that this is not quite a core set. Consider this example, still the one median, but all your data, most of your data is all concentrated in a small region. There's one point that's really far away. Okay, this happens to happen on the right as well. Then if you took a random sample and you didn't pick all your points, you're gonna miss that point. Point is that all the cost was coming from that far away point. This was really important to keep. So now when you're crossing here and you find the solution here, now you can't peel it back because there's this point that's contributing a lot, which you didn't capture in your course set. Okay, so random sampling doesn't quite work. And I guess just formally, the random sampling of the cost here is a high variance estimate. In some sense, if you missed that one special point, now your cost has changed dramatically of whether you had included it. Okay, but it turns out that actually this is the only problem with course sets. So in some sense, the issue was that uniform sampling is a high variance estimate on the cost of any particular clustering solution. So what am I going to do? There's a standard way to do this. It's called importance sampling, where you basically want to say, I want to sample the points proportional to how important they are in any potential solution that you could solve. Okay, so how do you do this? This is known as a sensitivity sampling, and I'm just going to change the way I perform random sampling. Okay, so here's the idea. For each point, I'm going to assign what's known as a sensitivity. Now, this is a complicated expression, but all this is saying, look, consider any potential solution C. And now, how important is X to that solution? So on the numerator, we have the cost that it's going to contribute. And in the denominator, you have the total cost for that solution C. And you're saying, how important is X in any potential solution? Yeah. Capital X is all your data set. So the numerator is saying the contribution.
Medians are medians. Are we picking like a point to be our center, or are we like doing the supremum over any point?
Yeah, so C is a candidate centering. This can be any point. So this expression is saying, what fraction of the cost does X kind of contribute in any potential solution? Okay, because in the numerator has the cost of X to C. The denominator has the total cost of the one median at C. And now it's saying over all C, how important is X? Okay, so what would importance sampling do? Once you write down the sensitivities, you're saying if this point X was really important, then this sensitivity is going to be high because there exists a solution for which that point kind of contributes a lot. And now what you do is you sample with respect to that distribution. Okay, this is changing the way in which you choose your important elements. So the way that the best course set constructions work, they literally come up and they write down the sensitivities for these points, and then they sample proportional to the sensitivity. Okay. Any questions? Yeah.
Intuitively, why isn't it enough to just care about preserving like the optimal solution? Like, why do you sort of want to do this over all possibilities?
Yeah, and it's kind of the same maybe chicken and egg problem where you want to preserve the optimal solution, but you also want to guarantee that your optimal solution doesn't change. You have to make sure that another solution's cost doesn't go down to overtake the optimal solution. So you can say, oh, look at the optimal solution, sample, but maybe there's another solution which you didn't preserve, and now the cost has gone down. Kind of that answer your question?
And here you don't care about whether you can compute sigma X efficiently or not because it's only an analysis.
Exactly, it's only in the analysis. But what's awesome is that actually there exist constructions for which if you sample with this distribution, only poly 1 over epsilon many times, you can kind of union bound over all these solutions. This is somehow the magic of corsets. Okay. So now what happens? You take a sample according to the sensitivities of each point. You're doing importance sampling. Now it turns out this thing is a coreset. Okay. And now in our paper, we don't really need to worry. There's this issue of the union bound. Like how do you union bound over all solutions? But this is something that's part of the prior work. There are kind of known techniques to do this. Okay, and then this, I mean, it kind of commutes. You've sampled, but now you sampled with probabilities that depended on the sensitivity over the original space. Still not necessarily the case that it commutes. But what can you say? Well, if you have the optimal solution in the original space, when you sampled with respect to the distribution of the sensitivities in RD, not necessarily the sensitivities in RT. But the way you set up important sampling is exactly so in expectation, these things are preserved. Right, so if you take the expected cost over the coreset of Wx pi of x minus y for any y, in particular the optimal one, what is Wx? This is t over the number of points times sigma x, and this expectation multiplies by sigma x over t. This exactly cancels out. It tells you exactly this. It's exactly equal. And for this, we didn't need to, this was true for the optimal solution. We have the thing in expectation. It's actually by Markov inequality. Kind of the Markov goes in the right direction. Right? Like you took a sample from some distribution, and the expected cost only went down. You lose a constant factor, but I've just proven that JL preserves the cost up to a constant factor. Okay, so in some sense, what happened? We started with the optimal solution. We decreased the cost by moving to the coreset. Here we use Markov inequality, and you lose a large constant. Here was a subspace embedding, which we did. And now here we use the fact that it's a coreset. So these arrows are 1 plus or minus epsilon. This arrow is a constant factor. Okay, so we have a large constant factor. So that's the first step. Yeah, is that clear? So what do I need to do? I just need to show that actually the sampling was pretty good, that it was a low variance estimate. Okay. And so what did I do? I sampled with respect to calligraphic D, the sensitivities in the original space. I know that what I really should have done is should have computed the sensitivities in the original space, sampled according to that. I didn't quite do that. I sampled according to the sensitivities in the original space. And now what I need to relate is sigma to sigma prime. Like make sure that these things are okay. And this is kind of where the paper gets a little bit technical, but I can use one more thing. I can use that JL preserves the cost up to constant factor approximation. Okay. And yeah, there's a small computation here to show that actually these sigmas are the same, assuming that JL preserves the cost up to constant factor approximation. And then in some sense you can sample a few more. So this gives you a bound on the variance. Now you just oversample a little bit more. Now you bring the variance down to again 1 plus or minus epsilon. Okay. So if you look at the paper, yeah, sorry.
So this is saying that if you oversample a bit more, then on the right also you get a valid coreset.
You get, yeah, so if you oversample a little bit more, you get a low variance estimate. The fact that you oversampled means that you need to increase T again. So the subspace embedding is now on a slightly bigger set. But this was always a coreset, so now I kind of tightened all the arrows. So if you look at the paper, we kind of go through this cycle twice. Okay, so the first time we just use Markov inequality, we kind of show that actually the cost is preserved with a constant factor approximation. And now the fact that it was a constant factor, you can use that to go back and say, oh, actually my sensitivities after I applied pi haven't changed substantially. So really the sampling distribution you did do was a low variance estimate for the cost in the optimal solution. Okay. Now what's nice is that I didn't really use anything about clustering. I just used the fact that these sensitivities kind of commuted and Markov inequality. All right, so that's the entire proof. I wanted to conclude with some open problems. And just to mention, actually, in this paper, well, Radenstein, they actually proved something much more surprising. So in this talk, I said that you apply JL and the cost of the optimal solution is preserved. Actually, we know that they proved that for any clustering, so any partition of the points, the cost is approximately preserved. Somehow the fact that we went through coresets, we had to look at specific kinds of partitions which came from these like Voronoi diagrams. We can't quite get the strong guarantee. But this kind of also shows up in the low rank approximation to some extent. They show that, look, if you look at your data and you think of your data as the like you stack the points and you look at the columns. So you look at basically the n-dimensional points, the n-dimensional points given by the columns of your matrix. Then the cost of any low-rank approximation of this subset is approximately preserved after you take these linear combinations. So somehow our proofs they don't preserve this stronger for all guarantee. So it'd be very interesting kind of to see. And more generally, so can you actually generalize this for projective clustering, even for the line, the K line that was already losing this log n factor? The reason is that the coresets for the K line approximation problem, they have a dependence of log n. And kind of you can tighten this arrow to pay a log factor in the size of the coreset. Yeah. Anyways, that was all.